Okay, so today's lesson is 6.4. It's the last one for this unit, and it's on vector components and applications of vectors. So this is going to be very familiar to any student who took either grade 11 or 12 physics. But don't worry, I realize there are students here who didn't take either, so that's okay. We are doing it from scratch. So applications of vectors appears a lot, especially in physics. I mean, usually when you do applications in mathematics, it's either physics or finance. But finance, money doesn't have a direction, so it's not going to appear anywhere in vectors. We just have, in our case, we could be dealing with maybe adding velocities, but one of the most useful ones is adding forces. So that's what we're going to look at. We're going to look at resultant and composition of forces. So let's say we had just two forces. A force is just when you push or pull something, really. So let's say we have two forces, F1 and F2. Maybe two people are pushing something. And so the resultant is the sum of those forces. Okay. Now the equilibriant is another term we're going to talk about. The equilibrium is a necessary force which would be required to put the system in equilibrium. Equilibrium just means that all your forces add to zero. Okay? Because in physics, when all your forces add to zero, you're in equilibrium and you maintain your state of rest or motion, whatever it is. There's no more acceleration. And so it's a very important factor. A lot of times if you have something hanging from a ceiling, it's in equilibrium, right? If you have a traffic light hanging outside above your street, it's in equilibrium. Okay, there's forces on everything, but if something's just at rest, all of those forces simply add to zero. Right now, if you're sitting down in a chair, there are forces on you, but they all add to zero because you're at rest there. So that's what we're going to look at doing today, by adding the forces and finding the resultant and the equilibriant. All right, so finding the resultant, we've added vectors before, so that's not too hard. And finding the equilibriant, well, if you get one vector, like in this case, here you have F1 and F2, so you finish your parallelogram and your resultant is this red vector here. The equilibriant would be a vector with equal magnitude, but in the opposite direction. That would make them add to zero. So this black vector here would be our equilibriant. Another thing I'm going to show you today is the other method that I've been telling you about, other than using a parallelogram to add vectors, and that's components. So we have two things that we can do the vectors, composition or resolution. Composition is just when we take vectors and add them together into one nice vector. Resolution, however, is the opposite of that. Resolution means we take one vector and split it into parts. And that's what components are. Specifically, components are, we would take one vector, let's take this vector F here, and we are going to split it into parts. So let's look at this vector F here, like that. There's F. Now we can split it into two parts. Specifically, we're going to split it into a horizontal part here. Oh, so close. And a vertical part here. So notice if we add this horizontal part to this vertical part, the resultant of those two parts is F. But what we're doing is splitting F into those two parts, which is resolution. And we have a horizontal part in our x-axis, which we will call f of x, and we'll just do a subscript x, and a vertical part in the y-axis where we will put a subscript y, like this. Does anyone have any questions with that? If there's no questions, then what I'll do is a little example problem right here. And I'll do it with two methods. One that we are now familiar with, our parallelogram, and the other one with components. So first, let's start with the parallelogram. So our problem is we have a ceiling and we have some mass hanging from the ceiling. So we have two ropes. This one, which makes an angle of 60 degrees with the ceiling, and this one, which makes an angle of 45 degrees to the ceiling. Whenever we have a rope that's pulled on and is taut, we say there's a tension in the rope. So the force on the rope is called tension. And I'm going to call this one T1 and this one T2. And of course, there's gravity pulling down on the rope. Now our mass weighs 20 kilograms. Now force, we don't use units of kilograms, that's mass. Force, we use units of newtons. And this would actually weigh 196 newtons. If you're unsure about what that would feel like, just imagine trying to hold 20 kilograms of weight in your hand. And the force required to actually hold it would be 196 newtons. Okay, so we have three vectors here, T1, T2, and this 196 newtons straight down due to gravity. And we need to figure out what T1 and T2 are. That's the problem. So we can do a parallelogram. So I'll just do an equal vector to T2 right here. Like that. Close enough. And 1 to T1 right here. That is terrible. Let me redraw those. It's also terrible, but I'm not going to redraw it anymore. So we have this equal vector to T2, this equal vector to T1. And of course, they're going to add to give this vector here. Oh, sorry for my drawing today. Okay, now this vector here, right, is going to be the resultant. And of course, this 196 would be the equilibriant. So the resultant and the equilibriant are going to be opposite, but the exact same magnitude, so that they are in equilibrium. So we know that T1 plus T2 gives us some value of 196. And we can also figure out that using this Z pattern, that this angle here is 45. And so together, the whole angle, this entire angle here, would be 105. There we go, 105. Okay, so let's focus on this triangle here. It doesn't quite meet, but that was my fault. Let's assume they meet real nicely, okay? And what we're going to do is the sine law. So this here is our equivalent to T2. Okay, this angle here, if you look at this little triangle here, that's a right angle triangle. And so this angle here would be 30 degrees. And so what we can do is we can say the magnitude of T1 over the sine of, and this angle here, again, if you look at this smaller right angle triangle, they would all add to 180. So if that's 45, this would also be 45. I'm just running out of room to write it. 45. So sine of 45 equals the magnitude of T2, just using the sine law. Okay, so T2 over that opposite angle, sine of 30, equals the magnitude of this resultant, which we know must be 196. all over the sine of 105. So from here we can just apply the sine law twice, once to solve for t1 and once to solve for t2. And we're done. So let's do that. So t1, we'll start with t1. So the magnitude of t1 equals 196 times the sine of 45, all divided by the sine of 105. And you'll get T1 to be about 143.5 newtons. Do the same thing for T2. Okay, so now we're going to use these two ratios here to solve for T2, and we'll get 196 times the sine of 30 all over the sine of 105. And when we do that, we get 101.5. So now I'm going to show you how to do the components method. I'm just going to get a little space here, and I'll redraw it so that we can see. So we had our ceiling, one rope, T1, one rope, T2, and then we had our 196 down, and we had our angles of 60 here, 60 degrees, and this angle here, which was 45 degrees. Okay, so if I'm going to do it with components, what I need to do is take any vector that's not perfectly horizontal or vertical and create a horizontal part and a vertical part. So the two tensions are not horizontal or vertical. So let's start with T1. If this vector is going up and to the left, then I will write two vectors, one that's going to the left and one that's going up. Like so. Ooh, somewhat. And if this vector is going to the right and up, then I will draw two vectors, one that is going to the right and one that is going up. I'm not doing a very good job with my straight lines here. Just like that. Okay, and what I can do is then, because these are right angle triangles, right, this one here and this one here, I can simply solve using SOHCAHTOA, using our trig ratios. So first, we know what this angle is, because we have our Z pattern, so that's 45. And this angle here is 60. And then the sine of 45 equals this y, or vertical component. So I'll just write it over here. Sine of 45 equals that vertical component, I'll just call it T2y, over T2. And I can rearrange this to solve for T2y. So I can say this vertical vector is just T2 times the sine of 45. And I can do the same thing with the horizontal. I can just set up a trig ratio and solve for the horizontal component, which would be T2 cos 45. And the same thing over here. This would just be T1 cos 60. And this would be T1 sine 60. Now that that's done, we can set up an equation, because the system is in equilibrium, so all of our horizontal and vertical components must balance for equilibrium to be true. So let's look at all of our horizontal components. So our horizontal components, we have this one and this one. So this one to the right and this one to the left. They must balance. So the one to the right must equal the one to the left. So I can say T1 cos 60 must equal T2 cos 45. And then I can come up with an equation for a vertical. So we have actually three vectors in the vertical. We have this vertical component of T1. We have this vertical component of T2. And we have this, the weight of the mass. So they all must balance. The two up must balance with the one down. So I can write T1 sine 60 plus T2 sine 45 must balance with that downwards 196. Let me just pause. Okay, continuing from here, what we actually have are two equations with two unknowns. Right, 1 and 2 and T1 and T2. So at this point, we're just going to solve two equations for two unknowns. So what I can do here is I can rearrange equation 1 to solve for T2. And I can say T2 equals T1 cos 60 divided by the cos of 45. And then I can substitute that into equation 2. And when I do that, equation 2, I get T1 sine 60 plus T2, which is what I'm going to substitute this in for, which is now T1 cos 60 all over the cos of 45. Just running out of room here. Times by the sine of 45. Flip the screen over. There we go. Times by the sine of 45 will equal 196. So I just substituted this into here. And now I have one equation with one unknown, just T1. And so I can factor out T1, right? And in my first term, I just have a sine 60 plus, in my second term, I have a cos 60. And then I have a sine 45 over cos 45. You can leave it as sine 45 over cos 45. Or if you really love trig identities like me, then you can just write it as tan 45. It doesn't matter. Your calculator will give you the same answer either way you decide to do it. Equals 196. Then you can divide both sides by that bracket, shove everything into your calculator, and you'll get T1 equals to 145. Sorry, 143.5. And that would be newtons. Then we can sub T1 back into equation 1 here. Okay, so sub into 1. And we would get T2 equal to 101.5. Like that. So the first one says we have two forces, 20 newtons and 40 newtons, act at an angle of 30 degrees to each other. Determine the resultant and equilibrium of these forces. Well, let's draw this. If I were to make this into a parallelogram, which is a nice way to do it because they already have it set up where the two tails are connected. So let's just finish the parallelogram here. Or I shall try to, because I don't have much space. Oh, I messed that up. Okay. Oh my goodness. Every time I go to lift my pen, I tilt it a bit. So just ignore the fact that that's slightly curved. Actually, let me try. Give me one more try because it's bothering me. Yes, okay. So here we finished our parallelogram. And if we connect both tails to both heads, that will be our resultant vector right there. Now the equilibrium vector would be in the opposite direction. I don't have enough room, but it would be in the exact opposite direction with the same length. Okay, but I can't make it that length because I'm out of room. But just for a visual, okay, this would be our equilibrium vector. I'll call it E. And this one is our resultant vector. I'll call it R. Okay, so because this is a nice parallelogram, I can tell you that this angle over here is 180 degrees minus 30, which gives us 150 degrees. This vector over here is an equal vector to this one. It's supposed to be. It looks slightly different, but it's supposed to be. Okay, and so we can use our cosine law to find the magnitude of r. So the magnitude of r squared will be equal to 40 squared plus 20 squared. Just going to zoom in. It's easier to write when I zoom in. Minus 2 times 40 times 20, going into the other question here, that's okay, times the cos of 150. Okay, so 40 squared plus 20 squared, that's 2,000. Minus 2 times 40 is 80, times 20 is 1,600. Times the cos of 150, which, I mean, if you don't have these memorized, that's fine. Just use your calculator. It's minus root 3 over 2. Okay, negative because it's in the second quadrant. You remember, like, cast rule, C-A-S-T? So the cos would be negative in that quadrant. All right, and to figure out what r is, we then have to square root both sides. So we'll get the square root of 2,000 minus, well, the 2 can cancel with that to give 800. So minus 800 root 3. Well, sorry, plus. Double negatives gives us a plus. And you'll get a value approximately to 58.2 newtons. Now that also means the magnitude of our equilibrium is also 58.2 newtons. But the question said to find these vectors. And so when you find a vector, you also need to figure out the direction relative to something else. So what I would like to do is figure out what this angle here is then, this angle theta. To do that, I'm going to use the sine law. I'm just going to go find some space. I'll just do it over here. So the sine of theta, okay, over that opposite 20 equals, we can use the sine of 150 over the opposite r, which we know the magnitude now to be 58.2. Rearranging and taking the inverse sine, just going to do that in one step because I'm running out of room, and I'm assuming you guys can do that. You get 10 degrees. So what you can say now is you can say the resultant vector is 10 degrees from the 40 Newton vector, and that would make this 20 degrees from the 20 Newton vector. And then similarly, you can calculate where the equilibrium is, because this whole thing would be 180 degrees. So if this is 20 and this is 10, you can say the equilibrium would be 160 degrees from your 20 Newton vector and 170 degrees from your 40 Newton vector. Okay, I just run out of space, so I'm not going to write that. So example 2 says a plane is heading due north with an airspeed of 40 kilometers per hour. When it is blown off course by a wind of 100 kilometers per hour from the northeast. If something's coming from the northeast, that means it's heading in the opposite direction, which would be southwest. Where here's your compass directions. If you remember the acronym, never eat shredded wheat, like that. So if something is coming from the northeast, then it's going southwest. So we have our vector here, southwest. And if we simply say southwest without being specific to the angle, that means it's perfectly southwest. And so the angle is 45 degrees, which would be half of 90. Okay, so we can draw these. Right? We're going to make our triangle, use our addition by triangle. So we have this vector, which we'll call v, okay, the velocity of the plane, going perfectly north. And then to the tip of that vector, we'll add the tail of the next vector, which is our wind. And then our resultant will be from the tip of the first vector to the tail of the last vector. So this is our resultant. Okay, and we just need to solve this. However, if you would like to see what it looks like as a parallelogram, I can always do that as well. And you can draw your north vector, and then you can draw your southwest vector, which would be connected tail to tail, and then just finish that off in a parallelogram like this, or something. I made that one a little bit too short, but you get the idea. And then your resultant vector is just connecting tail and tail to head and head, which is the exact same that I wrote over here, right? I just have this triangle only, which is the one we're going to analyze. So we know that this is 400. This is 100. And this angle is 45. So immediately I can just jump in and use our cosine law. So the resultant, or the magnitude of the resultant squared, is 400 squared plus 100 squared minus 2. Just going to run out of space. Times 400 times 100 times the cos of 45 degrees. So 400 squared, we have 170,000 minus 2, so 800 times what is minus 80,000 times the cos of 45, which is 1 over root 2. Okay, and square root both sides. Just doing this in less and less steps here. And we'll get the magnitude of r to be approximately 337 kilometers per hour. Of course, it's important to know how fast the plane is going, but it's also important to know where the plane is actually going. So we need to figure out what this angle theta here is. To do that, I'm going to use the sine law. So the sine of theta over 100 is going to equal sine of 45 over the magnitude of that resultant, which we got to be 337. And then you could multiply both sides by 100, take the inverse sine, and you'll get theta to be 12 degrees. So you can then write, therefore, our resultant vector is 337 kilometers per hour. And since we are using our compass directions, we know it's north, 12 degrees west. North 12 degrees west. Luna pulls on a rope attached to her sleigh with a force of 200 newtons, like so. If the rope makes this angle of 20 degrees with the horizontal, then what's happening is we're slightly pulling it up and we're slightly pulling it across. So the question says, with what force do we actually pull the sleigh forward with, and with what force do we actually pull it up with? So this vector here, let me zoom in. This vector here, we can split into components. Another reason why we do this in physics is because this clearly says we're pulling up with a little bit of force and across with a little bit of force, which we would want to know what they are separately. So if we split it up, if this is going to the right and up, then we'll make two vectors, one going to the right and one going up, like so. And that's a right angle triangle. So for part A, let's call this our force in X, and this will be our force in Y. So for part A, it says the force that pulls the sleigh forward. So for part A, we're going to solve for the force in X. And to do that, we're going to use our SOHCAHTOA trig ratio cosine. So the cos of 20 equals adjacent over hypotenuse, so the magnitude of fx, forgot my vector signs in the diagram, over 200. Rearranging, you get the magnitude of fx equals 200 times the cos of 20, which is 188 newtons. For part B, if we do the same thing, but we use our sine ratio, we'll get the magnitude for our y, or vertical component, to be 200 times the sine of 20, which will equal 68.4 newtons.